Okay, so good evening, everyone. This is Parul from AWA India. I welcome you all to the webinar on advancement in water treatment technology. We have three speakers today, Mr. Ame Ajit Pradhan, Mr. Rick Bacon, and Mr. Madhusudan Madhav Joshi. And we have a moderator, Ms. Shivani Dikshit Masotkar. I would like to tell you a brief about Ms. Shivani. Ms. Shivani is having more than 32 years of experience in water, wastewater, recycle, and desalination field. She has an experience in conceptual detailing of process design. She has done her BSc Technology from Nagpur University and she's a gold medalist. So over to you, Shivani ma'am.
Yeah. Uh, Good evening, friends. On behalf of AWA, I welcome all of you for today's webinar on advancement in water treatment technology. We all know that the recycle and reuse of water, wastewater, has become the need of the hour. There are various critical, difficult wastewater which need special advanced treatments. With scarcity of water and restricted discharge limits, and the need of the to diversify water supplies through potable reuses, which have necessitated a shift beyond conventional treatment. To address this, today we have three speakers with us. Let me introduce the first speaker, Mr. Ame Ajit Pradhan. Ameya is a process and field service manager in uh, Coach Separation Solutions. Amey has completed his master's in chemical engineering and working with Coach for last 12 years. He's looking after the process and field services activities for Indian subcontinent and Middle East region. Today's topic for Amey is submerged UF and for water and wastewater applications. Our second speaker is Mr. Rick Bacon. Uh, Mr. Bacon has been CEO of AMS since 2011 and has built its leadership position in online real-time monitoring of THM and trace metals. More recently, he had led the company's development of an innovative treatment technology that is replacing bulk chemicals, reverse osmosis, and ion exchange for the treatment of a broad range of drinking and wastewater contaminants. Prior to joining AMS, Mr. Bacon held a series of international leadership roles with US and European companies in the energy and technology sector. He holds MA from University of Cambridge and PhD from University of California, Santa Barbara. Let me introduce our third speaker, Mr. Madhusudan Joshi. Madhusudan is currently working as a consultant with TOEM. Mr. Madhusudan Joshi has a vast experience of 30 years in the field of membrane technology. He is currently active in training and consultancy work. I welcome all the three speakers to this today's seminar. I would also like to mention here that after this, after we finished all the three presentation, we will have a question answer session. Uh, Hope that is okay with all of us, so that we save a lot of time in between. I think I'm. Let us start the first presentation of Ameya. I welcome Ameya for the presentation.
Thank you very much, Shivani ma'am. Good day, everyone. This is Amya Pradhan. I'll be sharing my screen. Is my screen visible?
Amir, no. Should I present your?
Yes, ma'am. It will.
Yeah. Yeah.
So I'll be starting with a very basic introduction to what is ultrafiltration. Today's topic is submerged ultrafiltration for water and wastewater applications. So, what is ultrafiltration? I think many of you might have heard the name. You might have used the ultrafiltration membranes in various applications. So, ultrafiltration is basically a low pressure driven process compared to nanofiltration or an RO reverse osmosis system. It is used to separate high molecular weight compounds based on the pore size or the molecular weight cutoff. Typically, pore size ranges from zero point zero 0.01 micron to zero point zero 0.05 micron in an ultrafiltration membrane. In some cases, it is also distinguished based on the molecular weight cutoff. For example, 10,000 Daltons, 100,000 Daltons, etc. Ultrafiltration membranes are available in various configuration, be it hollow fiber, be it spiral wound or tubular configuration. The most common configuration usually used in the water and wastewater application is hollow fiber, but in certain applications, depending upon the type of the fluid that we are treating, the membrane configuration is selected. Next. So in ultrafiltration membranes, widely there are three types of configurations: tubular, hollow fiber, spiral. And as you can see, the tubular membrane has a bigger flow channel compared to hollow fiber and spiral. Because of this, the membrane packing density increases from tubular to hollow fiber and to a spiral membrane, meaning spiral membrane has a more packing density, so it requires a lesser footprint compared to the tubular membrane as well as the hollow fiber membrane. And the concentrate solids is also decreasing. In tubular membrane, we can concentrate the solids in much higher concentration compared to the spiral bound membrane. Next. So what is submerged UF? So many of you might have heard the term membrane bioreactor. So is it like a membrane bioreactor, MBR? So in a way, it is quite similar to an MBR based on the suction and not pressurized feed. In case of pressurized feed, we have a pressurized UF, we have a pressurized feed. Whereas in submerged UF, there is a filtration of only solids, and in MBR, there's a filtration of typically what we say mixed liquor wool suspended solids, that is MLSS or a biomass. In MBR, there is a recirculation. Most of times, a constant recirculation of MLSS from the membrane tank to biology happens. Whereas in submerged UF, solids are drained from membrane tank intermittently so that the solids concentration doesn't increase beyond a certain level in the membrane tank. In the submerged UF, as the name suggests, these membranes are submerged in a water or a wastewater, and these membranes can be placed in either a civil tank or a fabricated tank of metal. But most importantly, since we are using it for the applications, most of the times where there is probably an RO in downstream, we would require a proper coating on a tank wall so that there is no silt particles, there is no cement particles that enter into the membrane and that which can damage the membrane's properties. So what has basically changed in MBR membrane module to a submerged UF membrane module? So in MBR membrane module, typically you will have a gap between the membrane hollow fibers, whereas in submerged UF module, there will be less gap. The packing density will be much more higher. The same module frames are typically used. It reduces the choking capability because in submerged UF we are only treating the solids, not the MLSs, which can be in the range of 10,000, 12,000 milligrams per liter. Whereas in submerged UF, the solids can be in the range of 100 to 200 ppm, and in the submerged UF tank, it can be concentrated to around 1,000 milligrams per liter or 2,000 milligrams per liter. So a slight tweak in the membrane module design, that is what only requires in the compared to MBR membrane module to a submerged UF module. So what are the typical applications of submerged UF? So wherever, in principle, wherever there can be pressurized UF which can be used, submerged UF will find its application there. Be it a tertiary treatment where there is a where we can position for a tough to treat waters where secondary clarifier is not working effectively. There is an upset in the secondary clarifier. You have some sludge carryover, some small biomass carryover going to the downstream equipment. This submerged UF can handle the. It can also be used in a surface water where there is a high TOC loading or turbidity spikes, specifically sometimes in the river water applications, or in it can be for the TOC or color removal in surface water, which can be treated with some coagulant dosings. It can also be used for iron or manganese removal if the water is having a high content of iron or manganese. So with the help of the oxidant, we convert the dissolved form of iron or manganese to a suspended form, and the submerged ultrafiltration will do the filtration based on the pore size and molecular weight cutoff. And most common application is the RO pre-treatment. With RO pre-treatment, since this is an ultrafiltration membrane, what is used in submerged UF, it can give you SDI less than 3 on a continuous basis, and it can also be used for seawater desalination. In seawater desalination, there might be some modification required in case of the module frame that is used. Typically these module frames are of stainless steel. It can be SS316, but in certain seawater applications, it can be changed to say duplex frame or super duplex so that it can withstand the higher chloride concentration appearing in the seawater. So, what is the so what does KSS offers in Puron in submerged UF? We call it as Puron HF. It's a high flow membrane modules. It's available in different configurations. 480 meter square, 960 meter square, and 2650 meter square. So based on various flow rates, different modules can be selected, and the different modules can be arranged in a single tank or a multiple tank depending upon the redundancy required by the end user. So it can be 1 into 100%, 2 into 50%, or 4 into 25% configuration. So whichever is required by the end user, and there can be multiple membranes arranged in a single tank, or multiple membranes arranged in different tanks to have a redundancy. So what does the Puron HF has? So it is basically a single header membrane module that is used in the Puron HF module. Here we have the single potted membrane. It's an hollow fiber membrane which is potted only from the bottom of the membrane, and it is free at the top of the membrane, which is sealed at the top end so that there is no solids entrance into the membrane fibers. These membranes are operated in outside in mode, and it has a braid inside or a reinforcement which gives the strength to the membrane. And this is similar to a membrane bioreactor where the membrane is used for at a very high solids concentration. In submerged UF also, there can be certain spikes sometimes in a river water or surface water or tertiary treated water where secondary clarifier is not functioning properly. So this braid or this reinforcement gives strength to the membrane, and it, since this is an ultrafiltration membrane, it rejects the bacteria, the colloidal solids, suspended solids, and only the water with water with treated water with turbidity less than zero point 0.5 NTU passes through the submerged ultrafiltration membranes. So this is how the air scoring happens. It's a single header design and a central aeration. In central aeration, there is an aeration right at the center of each bundle, which gives which keeps the membrane clean. So whatever suspended solids, whatever uh, im- foreign impurities like some fibers, which can be expected in treated sewage water, or some hair particles, this which can appear in wastewater, that can be removed from the membrane bundles. So due to this single header and central aeration, there is a reduced clogging and sludging, and this helps in the reduced energy consumption, because as we know, whenever we talk about any membrane technology, the major concern from any of the user is the energy consumption. So since we have this single header and central aeration, the header, the energy consumption required for the submerged web application is at very low volume. So there are different types of membranes in hollow fiber configuration which are available. There can be double header membranes which are potted from bottom as well as from top. And what KSS uses is a single header and central aeration technology, which I just briefly touched upon. So due to this, we can have a pre-screening which will be probably 2 mm for the submerged ultrafiltration membrane, so that we don't want any large particles going into the membrane's tanks. Next. So how does this membrane system operates? This can operate in a dead end mode, or it can operate in feed and bleed mode. So what are the different steps that operate in submerged ultrafiltration system? Mainly there is a filtration and there is a backflush or a backwash. In backflush, there can be various steps like pre-aeration, backwash, and the actual backwash with the treated water. Then post-aeration, just to clean the membranes so that whatever suspended solid that is getting accumulated in the fiber bundles, that can be cleaned. And then partial or full tank drain, depending upon the solids concentration in the submerged web tank. Because when we are operating in a dead end mode, after every cycle of filtration, the solid level in the submerged web tank will increase. So we want to control that level, which should not go beyond say 1,000 milligrams per liter or 2,000 milligrams per liter. And once it reaches that level, there is a tank drain. It can be 5% or 10% of overall volume, or it can be complete tank complete tank drain. And unlike any other membranes, uh, it has required the chemical cleaning as well. It is a maintenance cleaning with sodium hypochlorite, and other chemical is the citric acid. Sometimes HCl, hydrochloric acid, or some H2SO4 also can be added. And there is a more rigorous cleaning called recovery cleaning. In filtration, we do the suction with the help of the permeate pump, and filtration steps can be varied from 20 minutes to 45 minutes based on the feed TSS. Then comes the backwash. In backwash, there is an aeration step, as I said, pre-aeration, just to loosen the suspended solids attached on the membrane fibers, followed by the actual backwash, where a small quantity of water will be used for doing the backflushing, which is similar to pressurized ultrafiltration membrane. Next, then followed by the post-aeration and the membrane tank partial or a full tank drain based on the suspended solids concentration. So backwash can be anything in the range of 30 to 60 seconds. And in backwash, the water flows in the reverse direction compared to the filtration cycle. It is from the inside out, and it restores the baseline transmembrane pressure. Next. Aeration again, it's through the coarse bubble nozzle, which is located in the center of each fiber bundle. So it keeps it removes whatever suspended solids or any foreign particles trapped in between the fiber bundles, and it cleans the membrane fibers and helps in restoring the, the transmembrane pressure and keeps the membrane clean. Partial drain, again, I mean, it can be 5 to 10% after every backwash. It is to be completed typically in 10 to 30 seconds, depending upon whether it's gravity drain or pump drain. Both options are possible. Then system is again ready for the filtration. This is a typical chemical cleaning where the chemicals are introduced from the inside of the membrane fibers, and whatever suspended solids that is attached on the outside walls of the fibers is removed. So cleaning efficiency, like any other membrane technology, it depends upon the water temperature, what is used for the cleaning, or the chemical concentration, and the time, the soaking period, which is there for the membrane cleaning. Maintenance cleaning, it is done typically once in a day with sodium hypochlorite and maybe citric acid in a preset duration. It takes around 20 to 30 minutes in a day. Recovery cleaning is more rigorous. That typically happens once in 3 months or once in 4 months for the effluent treated water, or in surface water, it can be once in probably 6 months or once in 8 months. Next. So in summary, what is submerged UF and pressurized UF? So broadly, submerged UF can handle higher TSS because it is submerged and it is an open membrane, so we can clean the membranes. Whereas a pressurized UF, it is an enclosed in a housing pressure vessel, so can be cleaned only chemically. Submerged UF can be cleaned physically. It can handle higher TSS because of the higher packing density compared to pressurized UF. It requires a less footprint compared to a pressurized UF. And due to this, the lower energy consumption, since we can feed it directly by gravity from a clarifier in the upstream. So that was a short thing from the submerged UF. Thanks everyone again, and we'll wait for the next speaker.
I request Mr. Rick to take over the presentation.
Good evening,
Mr.
everybody.
Rick?
Yeah, I'm here. Good evening, everybody. Let me just share my slides with you. Okay, I realize we're running a bit behind, so I'll go through this quickly. So this technology is very suitable for the removal of arsenic, but it's also suitable for removal of several other metals from both drinking water and wastewater. But I'm going to focus here on arsenic. It's an issue of major concern in India, I know. So traditionally, there have been two types of technology approaches to treating for arsenic. One is the use of reduction, coagulation, filtration, usually based on ferric chloride, and the alternative is filtration. Both have serious disadvantages. Ferric chloride, largely because it's very toxic to handle. It's the nature of the chemical itself is a variable quality. It often contains co-contaminants that themselves may be heavy metals. Reverse osmosis, as many of us are aware and we've just heard, filtration is energy intensive. Something has to be done with the brine afterwards, which includes cost, which adds cost to the process. There are interferences which may reduce the effectiveness of this type of filtration, and need, as we just heard, for cleaning chemicals. Both systems have high latency, which is important where you have stop-go wells. It takes time for these systems to come back into equilibrium. You definitely need trained personnel, and generally these systems are not heavily automated, and because of their energy intensity of either transporting chemicals or electricity use for the reverse osmosis, have substantial carbon footprints. Electrocoagulation has been talked about as a way for treating for arsenic. Electrocoagulation has its applications, but it's limited technically for a number of reasons that I won't spend a lot of time on here. But suffice to say that it's not really suitable for drinking water applications, largely because of the need to maintain the electrodes in pristine condition. Otherwise, there's a risk of producing toxic byproducts. And it's very difficult to control the pH of the process, which in the case of arsenic is essential to achieve maximum removal levels. So our system looks similar to electrocoagulation in that we are taking the influent from a well, but in this case we take less than 1% of the actual produced water and run it through a generator into which we dissolve electrolytically under very tightly controlled conditions ferrous reagent. That ferrous is converted to ferric, and before injecting into the contactor we can adjust the pH in order to get optimal removal of arsenic. And then we follow the standard RCF process of coagulation filtration, and the whole system is monitored both on the influent and the effluent by an online total arsenic analyzer. So we have total control of the process. It means that it has very low latency, and we achieve very high levels of arsenic removal far more effectively than the alternative technologies. This electrolytic process is driven by Faraday's law. We know that depending on the amount of current we provide to the electrodes, we will produce a given amount of ferrous. That in time will oxidize to produce a coagulants or absorbents. It's very compact, it's in situ, and very economic in terms of power use. So this can be operated with renewable energy sources, and the ferrous, if required, can be stored and used at a later date. So when renewables are not available or off-peak electricity is not available, then that store of chemistry can be used essentially as a battery of those energy sources. So this, on the right, you have a picture. On the right-hand side of the picture is the online generator, and in the center of the picture there you see the cell. That's the contains the, in this case, low carbon steel, controlled quality. An electric current is passed across the plates and they dissolve progressively. We can set this up with either food grade tin or certified steel. And on the table there on the left hand side, you can see the different two primary configurations of the generator there in the middle. It either contains 4 plates or 8 plates. In the case of using tin, which is not the case here, but would be the case if we were looking to remove hexavalent chrome, you can see how much water can be treated very effectively using tin. So in this case, 4 plates would treat 64 milliliters, 8 plates 160. On the right-hand side of the table, you see the amount of iron that can be generated per day, 5 kilograms or 10 kilograms, the concentration of the reagent that's produced, 4,000 ppm, and then the volume of water that can be treated with those plates because they progressively dissolve and are then replaced. So 8 milliliters in one case, 19 milliliters in the second case, we're at 8 plates. And so depending on your flow to be treated and the amount of arsenic present, it's possible to work out the autonomy of these the system. And obviously for bigger volumes, we would have modules in addition to the single module. But in small treatment systems, this is obviously provides a lot of autonomy for a long period of time. The technologies I mentioned can be used for treating a wide range of contaminants, but in this case, I'm just going to talk about arsenic, where we've done a number of demonstrations, independently operated, and we've been reducing significant levels of arsenic to below 3 ppb, which is comfortably below the regulatory limit and enables blending where that's an opportunity to reach the regulatory limit, which, as you all know, is 10 ppb. We've done a number of case studies. The system has been approved by the US NSF for 60 and 61, so it's entirely suitable for drinking water. And there are a couple of links here, which but you would find them on our website as well, indicating the flows that we were treating, the amount of arsenic that was being reduced, and also the amount of silica that was present. The reason for that is because silica is a co-contaminant that impairs the use of other approaches like ferric, like ion exchange, or even electrocoagulation. And this is why controlling pH is very important. So we were comparing here at one of those case studies the performance of ferric chloride to remove arsenic, and that's the orange line, and with continuous monitoring. And then the blue line is where we were treating with on-site produced ferrous. The interesting thing is why we were able to get to below 3 ppb with the on-site generation system, and that's because we were able to control the pH. It's impossible to control pH where you're either using ferric chloride or electrocoagulation. It's very possible because we're dealing with a side stream with a very small amount of flow through, and therefore we can adjust very tightly the pH. And that enables us to operate under optimal conditions and therefore reduce arsenic to, as I said, 3 ppb. Overall, the efficiency of the system is also greater than bulk ferric chloride. On average, we dosed 30% less than the comparable amount of ferric chloride. So you have that produces a number of benefits. Firstly, you're using less. Secondly, you're producing less sludge, and there's far lower risk of ion carryover after filtration. One of the unknown facts about ferric chloride is that, well, firstly, how it's produced. In general, most parts of the world, it's produced by dissolving scrap metal in waste industrial acid. And it's very worthwhile looking at the actual chemistry of ferric chloride that's bought in bulk. One of the most surprising results of our research was that, and we repeated this on a number of sites, is the presence of manganese. And this is showing again the bulk ferric chloride had a presence of around about 30 ppb, which is getting very, very close to the proposed EPA limit for that contaminant. For on-site generated ferrous, we were using certified steel, so virgin steel with very, very low manganese levels. So we're not producing a contaminant, we're not introducing a contaminant into the drinking water through the use of the remediation method. And this is an analysis of ferric chloride, the same ferric chloride you've just seen a few minutes ago. And as you can see, it has very high levels of contaminants that you certainly don't want going into the drinking water, but more particularly when it comes to backwashing filters, this will end up in sewerage plants, many of which are not set up to remove these contaminants. So in the left-hand column, you see what's found in ferric chloride, and I would encourage you to analyze ferric chloride if you're using it compared to the ferrous reagent on the right-hand side. Everyone is interested in costs, quite rightly so. It's very important to look at both operating costs and capital costs, which we've done here. And again, based on very detailed analysis of alternative treatment systems, on-site generation of a reagent from certified steel is much more cost effective, both in terms of capital as well as operating costs, than the traditional treatment methods that you'll be aware of. We have a very quick to deploy demonstration system. You can see the dimensions of it. It's like a large closet. It contains all the key operating components that you saw in the full-scale picture, the galvanostat, which controls the current, HMI, which can enable you to remotely monitor the system. The generator in the middle, it's obviously very small because it's this is a demonstration pilot. Nevertheless, it can treat 20 liters a minute. So whilst it might be considered in some situations a demonstration unit, for some situations, it could be a full-scale unit. Gives you an idea of the compactness of this technology. It makes it very suitable for small systems where there isn't personnel present to take care. It can be fully automated and fully controlled. So wide range of benefits from the use of this system. Substantially lower lifetime costs, fully automated. The precursor is of control quality, certified, which would not be the case with ferric chloride. It does not produce toxic waste streams, and we have very low process water loss. Eliminates the need for transporting, delivering, storing toxic chemicals. Can be easily scaled up to plants of substantial volume, or scaled down the small treatment plants. It's highly efficient, so we can use renewable energies, and it's very robust and suitable for stop-run mode, and has been demonstrated in the US to be in a very effective system, and several systems are now being in the process of design and implementation. Thank you very much indeed.
Thanks, Mr. Rick. Now I request Madhusudan to make his presentation.
Hello, is my screen visible?
Yes, Madhusudan.
Yeah.
You have shared your entire screen. I
Yeah.
request you to kindly share the presentation part of the screen.
Yeah. Am I sharing the presentation now?
Not yet, Madhusudan. You should-
Some problem. Maybe you can start from your side.
I'll just check whether I have. Yeah. Should I?
Yeah, please.
Is it okay?
Yeah. Yeah. Sorry for this little disturbance. Good evening to you all. My presentation today is on high temperature RO membranes. In my presentation today, I am going to discuss about why there is a limitation on temperature for a conventional RO membrane, how much temperature a high temperature RO can handle, and some real life case studies where these high temperature RO membranes were used. Next slide, please. A typical temperature allowed for a conventional RO membrane is 45 degrees centigrade. Actually, the limit is for both temperature and pressure because temperature and pressure together affect the RO membrane. Let us understand what is the effect on the temperature and pressure on various parts of RO. In this slide, you can see three figures. The right-hand side figure is for a RO membrane which is cut open. So RO membrane, when it is cut open, you can see that there is a core tube at the central, and to this core tube, number of leaves or envelopes are attached. So these leaves or envelopes are like a bag made up of RO membrane. The water is flowing at high pressure across these envelopes. Then the permeate enters inside this envelope or leaf, and a permeate carrier is placed inside this leaf, and the carrier is attached to the core tube at the center. So this is how the membrane is constructed, and this whole assembly is rolled around the core tube. The figure on the left hand side is a magnified view of a reverse osmosis membrane, which is made up of three parts. The topmost layer is polyamide, which does the job of salt rejection. The middle layer is a porous support of polysulfone, and the bottommost layer is polyester non-woven fabric. So in short, the RO membrane is made up of three layers. That's why it is also called as composite polyamide. Now let us understand what is the effect of temperature on these parts of a membrane. First, let us consider the RO membrane sheet. As you have seen that the middle layer is made up of polysulfone porous support. So under effect of high temperature and pressure, this support gets compacted and its porosity reduces. And when it happens, the permeate flow going into the RO membrane also reduces. Or in other words, to get the same amount of permeate flow, you need a higher operating pressure. So that is the effect on the membrane sheet. The second effect is on the permeate carrier. Under the effect of temperature and pressure, this permeate carrier collapses and the membrane gets embossed inside the permeate carrier. This increases the resistance of a permeate flow into the core tube, and due to this additional resistance, the pressure required to get the same amount of permeate flow also increase. So this is the second effect on the permeate carrier. And the third effect is on the core tube. You can see that the core tube has a high salinity feed water on the outside, while low salinity permeate at a low pressure at inside. So when this core tube is subjected to a high temperature and pressure, it collapses and the membrane gets damaged. Due to these three reasons, there is a limit on temperature given by all the membrane manufacturer, which we have seen is 45 degrees centigrade. Next slide, please. When high temperature RO membrane are constructed, these shortcomings are taken care. First of all, the permeate carrier is designed specifically. It is a stronger carrier. It can handle higher temperature and pressure. And the second change which is done is in the core tube, which is also made to handle higher temperature and pressure. And with that, the high temperature membranes can handle temperature up to 80 degrees centigrade. I will take your attention to the graph here. The operation of temperature and pressure are inversely proportional. This means when I am operating at a higher temperature of 80 degrees centigrade, my operating pressure cannot be more than 20 bar. And if I am operating at a temperature of say 60 degrees centigrade, my operating pressure can go up to 50 bar. So depending on my operating temperature, the limit on operating pressure is also set. Next slide, please. Now I am taking you through some real life case studies. The first case study is in the oil and gas industry. There are type of crude oils which are difficult to extract. For such oils, steam is used. So there is a method called SAGD, steam assisted gravity drain, in which a steam is injected inside the earth, and the crude oil viscosity reduces, and a mixture of hot water and oil flows out. After oil is separated, the oily water, what remains, is called as produced water. It is at a higher temperature of 85 degrees centigrade. Next slide, please. No, one before this. I think anyway, you are not putting the latest presentation. In the treatment of produced oil, first it is treated by electrocoagulation. Then it is passed through a ceramic UF, because normal UF cannot handle the temperature of 85 degrees centigrade. And this is followed by a 2-pass high temperature RO, which produces a permeate which is good enough to put into a boiler. And the steam generator is reused back for crude oil extraction. Next slide, please. The second case study is about recycle of laundry wastewater. Laundry wastewater recycle is not a new application. A typical system uses a wastewater at a temperature of 50 to 60 degrees centigrade coming out from a laundry. It is cooled and then treated in UF and RO. However, with the invention of high temperature RO membranes, you are not required to cool that water now. This water can be directly treated in reverse osmosis, and about 75% of the water can be recycled back into the laundry. So you are not only recycling back the water, you are recycling back the energy also, because permeate coming out of the RO is at the high temperature. Next slide, please. The third case study is in the biodiesel industry. This type of application can be used in any industry where the last step in the manufacturing is evaporator. In a biodiesel industry, the evaporator contains glycerin, and this glycerin give a load on the biological treatment, because it is high on COD. So this evaporator condensate was treated to a high temperature RO. The RO concentrate, which is high on the organic, is recycled back to the evaporator, and the permeate, which is low on the organic, was used in other process areas in the same industry. So this way, not only the glycerin is recovered, also the water which was going into the biological treatment is also saved, and the load on the biological system is also reduced. Next slide, please. Yeah. With this, I come to the end of my presentation. Thank you very much for your attendance. And I also thank Nitto Hydronautics for providing the material for my presentation. Thank you.
Madhusudan, would you like to share the two slides which you said changed today?
Anyway, for saving the time, I will just discuss that application, the fourth application which was missing in the slide.
Okay.
It is in the sugar industry.
Okay.
In sugar industry, the cane juice is evaporated. The typical concentration of sugar in the cane juice is about 13%, which is taken to 65% by a process of evaporation.
Is this the slide you are talking?
No, this is the one. This was in the produced water. You can go to the last slide. Yeah. Yeah. So in a sugar industry, the cane juice have 12 to 13% sugar, and in the manufacturing, this juice is concentrated to 65% with the help of evaporators. However, the load of evaporation can be reduced if RO is used as a first step of pre-concentration. So the typical scheme is in sugar industry, there are clarifiers which operate at a temperature of 90 to 100 degrees centigrade. So this hot cane juice is first treated in a ceramic UF to remove suspended solid and the waxes. Then it is taken to a heat exchanger to cool down to 70 degrees centigrade. And then it is fed to a high temperature RO, which concentrates the juice from 12 to 13 bricks to 24 to 25 bricks. And this way, about 40% load on evaporator is reduced. Yeah, that was the missing presentation slide. Thank you.
Thank you, Madhusudan. It was a very nice presentation.